Okay.
The audio quality is significantly better.
Significantly better. Okay, so now I'm
Yes.
using a mic. If you guys, oh, you guys cannot see me. So now I'm using a mic, and I'm hearing you guys much better because I'm using the audio of the TV, so I can increase the volume, decrease the volume. So it's all on HDMI. So it's yeah, I think this it's much better than earlier. Earlier it was very crude. So,
Sounds much
yeah.
better, so that's good.
Yeah. Still, things can be improved a lot, but yeah, I think the limited effort I can put into these things and my abilities too. Yeah. Okay, so how are you guys?
Good.
How's that? How is this?
It's
Have you
not
got news?
fun, but yeah.
Not fun. Okay.
But we're here.
Yeah. Yeah, I don't know. Yeah, what can I say? Yeah, I cannot help much. That's my point on these things. But yeah, I think I should repeat this. I hope I conveyed this better earlier. If there are any you guys feel that the current circumstances is affecting you, I should point out that I'll be lenient in the course. From the understanding I've had or impression I've had from you guys is that you guys are all serious and you guys have been working hard until this started. And even now you guys seem to be working hard, but I'm sure you guys must be facing something or the other which is different from earlier. Everything is a change. So I'll be surely lenient, but so don't give up just because of the circumstances change. So don't give up on it. So I'll be lenient, and even there are lots of decisions taken at the university level. So I think people understand, they try to do something, but at the same time, fairness comes into picture. One has to do something that doesn't benefit someone more than the other. So those are the factors that comes into picture in these kind of decisions. So yeah, so if you have anything, feel free to tell me. Even otherwise, I'll be lenient. Okay? So I hope that conveys the point. Yeah, but we'll have the midterm. Having said all that, we'll have the midterm as usual. But don't get stressed out about that. Take it like a homework. Don't don't feel overwhelmed about what's happening. Okay, not what's happening in this course. The other things I cannot help. But at least from the course, and this is not priority. I think life is better things, more prior things are there. Okay, so that's my. Hopefully it helps. Yeah, is there light enough? Yeah, I think so. Okay, so we have. Yeah, so again, homeworks. I have not received all the homework from you guys. Don't. My only advice is that don't pile up. Like you can take more time, but don't pile up at the end. I see that all of you guys are working, so I have no complaints at all. So take your time. You guys meet me often enough, and it seems like you guys are all trying. So, so that's okay. But remember, at the end, it will pile up. So it's only one homework. I think most of you. I think some of you are 6. I think so. 6, 7, 8. So now there is a 8th homework that's due. Correct. Currently, we are on 8th homework. Is this readable?
Mm-hmm.
And zoom in also. Zoom in. I think zoom in works better. I think. And I haven't graded. I think I at least have homework 6. I think from some of you guys, I haven't graded either. So that's also. Okay, and we have midterm 2. So this is on April 13. So yeah, a small change of plan here. I said that it's going to be a take-home exam. and that's how I want to keep it also. But there is one thing I was thinking. See, usually the exam has this purpose that you guys work for it, right? You guys prepare for it, and that leads to some kind of learning at your end also. I know it is all hurried up learning, but still there is some kind of learning that happens there. And if I make it a take home, there is a chance that some of you may not just study. It's only the 5 problems that I'll give you that will be attended upon too. So to solve the problem, I was thinking one problem I'll make at the time, and it is only for 1 hour, and you get only 1 hour for that, and you submit it. Do you see what I'm trying to say? Like most of it will be take home, but one problem which will be simple enough, relatively significantly simple enough that you do it, or you get only 1 hour. Still you work on it and then return it back. We opened only 1 hour before the exam is due, so the due date becomes rigid. The exam, most of the exam will be available earlier. Last question will be available in 1 hour. You have 1 hour to attend to it. My point is that, so you'll prepare for that one question, and that's even if you open the book and go through the whole thing, it serves the purpose kind of. Does that make sense? What I'm desiring and why I'm doing it?
Yeah.
Yeah.
I'm not entirely sure your method, like what, so you're saying the rest of the questions you will have the day before or something, or like 2 days before?
Yes.
That one
So let us,
question,
and yeah. Okay, go ahead.
beginning of the class?
Yeah, so let us say, so first I will make the due date clear. So let us say that since we have a class session for it, but I wanted to teach on that day. So that was one thing. So how about this? I will make it due. Yeah, I think the only possibility is that during the class. So I will make it due at the end of class period on April 13th. And one question will be available to you at the beginning of the class.
So
most of the paper will be available to you about 48 hours before the class, or maybe even more.
But then how will you work if you're in the class during that time?
Yeah, so that's my point. I think the only point I see is that I don't teach at the time. So you will work at the time. I was hoping I can do it during, I teach that time, but I'll have to give up on that because I feel this is important in the sense that you guys work for that question. How much ever less work, at least you work. Even thinking about the exam, I feel you collect your thoughts on the topics. Everything I think helps.
There won't be a class that day on April 13th.
So there won't be a class at that day. It will be, you will be taking the exam, and there will be only one question on that, so it shouldn't be very stressful and relatively simpler, significantly simpler. It's more to make sure that you've got the whole, or you're in the class, just to make sure that you know what's going on, what are the topics going on. So, you see the point, Angela?
Yeah.
Right. Any other suggestions you guys have? Is my motivation clear why I am doing it?
I think so.
Yeah, the motivation's clear.
So other classes also I plan to do that. Yeah. Okay. So let's go back to the Kepler problem. We discussed a lot of qualitative features of the Kepler problem. So let's try to get as much details as we can from the analytic expression. So first we have to derive the analytic expression, and everything we said last time will come out of those expressions. So, so let's change this. Okay. So we're doing Kepler problem. And it doesn't write. I call it the Kepler problem. I think it's reasonable. to call that. Yeah. Okay. So two masses, M1 and M2, right? M1 and M2, and there is R1 is the position of the first mass, R2 is the position of the second mass, R2 minus R1 will be this, right? So that's R2 minus R1, and everything turns out depending only on that difference in the positions of the two masses. And we said in general, the Lagrangian depends on R1, V1. V1 is the derivative. We have used it sufficiently, so that's specified, I suppose. R2, V2, right? That's what it depends on, and that's equal to half M1 V1 square plus half M2 V2 square plus it should be minus of the potential, but the potential itself is negative sign. So it is G M1 M2 over R2 minus R1 or R1 minus R2. It is the magnitude that it depends on. Right? That's your Lagrangian. Right? Okay. So immediately we defined the center of mass coordinate somewhere in between. If it was a very generic system, if it was Sun and Earth system, the center of mass comes out to be very much almost the same as the position of the Sun itself. So it doesn't matter whether you consider that or not, but in general, there is a center of mass somewhere here. So we consider the coordinates R is equal to R1. I think we did R2 minus R1. It is R2 minus R1. Right, and the center of mass is M1 plus M2 times the center of mass R, or the position of the center of.
So are you have R1 minus R2, and then you have R2 minus R1 for.
Oh yeah, this is magnitude, right? It doesn't matter.
Okay.
So I can change this
Okay.
if this helps. This is R2 minus R1, right?
Yeah, I guess that's true.
Since it's a magnitude, it doesn't matter, right?
Mm-hmm.
Right, but when I'm doing the force, then it matters. Then I have to talk about force on which one, right? Accordingly, it will change. So Lagrangian doesn't depend on the force definition itself, so it's okay. Okay. So I kept R2 minus R1. Actually, it doesn't matter. I can do R1 minus R2 here right away, because mainly I haven't told you which one is Earth and which one is Sun, right? Eventually, I would consider one of them to be the Earth, and then it's convenient to choose the one that is moving to be the lighter one is easier because that's what will be dynamical. The Sun doesn't move much significantly. So that was my idea that, oh, I had it in my head that, oh, this is going to move, but I haven't told anything here. Right? It's completely symmetric at this point. Okay. Mm-hmm. In that sense, it doesn't matter which one. So this is M1 R1 plus M2 R2. So that was our coordinates. That's called the center of mass coordinates. So basically, we do one more step, which we haven't done yet, that we can go and sit at that point. Otherwise, there could be a coordinate system here. This could be moving with respect to the whole system. But if we set it so that the center of mass is at rest, then it's nicer, or one of the motion doesn't come in. So in those coordinates, then the Lagrangian becomes, we said, R, right? And then there is a velocity v. So this is capital velocity v. That is the center of mass motion of this, or the velocity of the center of mass. Then there is small vector and then a small v. And we showed that this doesn't depend on the velocity. Like in general, we would expect that that would have depended on that, but that's the advantage of the center of mass frame that, oh no, did I say that? I said it wrong, right? What is wrong?
It should depend on the center of mass.
Yeah, it should be independent of the center of mass, not. So it's independent of the position of the center of mass, but it depends on the velocity. So let me write that as dr by dt, so that there's no confusion. So in general, it will depend on 4. I'll strike off one of them immediately. So that comes out to be half m1 plus m2 dr by dt square plus half mu. We defined mu, velocity square, where mu was, what was mu? 1 over mu is equal to 1 over m1 plus 1 over m2, right? Like in mathematics, this is called, what is this kind of average called?
What kind of average?
Huh?
What's the question?
So if you're doing, I can write somewhere, yeah. So if you're doing m1 plus m2 over 2, that's called the average of masses, right? Or yeah, that's average. But what is 1 over m1 plus 1 over m2 called? There's a name and there's a technical word for it. Huh.
Probably something
Okay,
like
sorry.
reduced average or something.
Reduced average. No, in physics we call it the reduced mass. That's correct. Good. In mathematics, it's more generic. There's some word. Yeah. Okay. Sorry. Oh, extra. But no, don't submit it here at the end. If I ask you for, so submit it. Okay. So it's a it's a word for that. And, so the 3 averages. One is a normal average that we always, one is this, and then there is a harmonic mean. Harmonic mean, and this is forget it. Yeah, okay, doesn't matter.
Oh
So,
yeah. Maybe you're right. Harmonic.
So this
Yeah.
is not the harmonic mean.
Geometric, harmonic, and
No, yeah, I think geometric. Yeah, I think this is, one is geometric, one is a standard, and the third is the harmonic mean. There are 3 averages. Yeah, I think so. Okay. So now I'm confused even when I think it is geometric. Arithmetic mean, geometric mean, and then the harmonic.
geometric is square root of m1, m2. That would be geometric. I think you're right. This is harmonic. I think you're right. That's harmonic mean.
This is harmonic. Okay, so I thought this will be geometric. So this is harmonic. So square root of a product, first multiply and then take square root. That's geometric. Okay,
Geometric,
okay.
yeah.
That helps. Okay. 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 So in terms of those coordinates, this becomes plus, that is plus, I suppose. So this is G m1, m2. Now its magnitude, notice. So I'll specify, I mean, usually R, right? That's sufficient. But just to stress on that fact that it's a magnitude of this magnitude of R. Notice this does not depend on the position of the center of mass. So if you're talking about a galaxy, it doesn't depend on where the galaxy is or where your coordinate system is. That's what it means. It's practically saying that it's on that. So this can be struck off. So those and on the center of mass.
I think we're losing you. Your mic is, we can't actually hear you at the moment.
You're breaking out.
Hello? Is it any better now?
There you go. Yep, you're back.
Okay. I have to keep it outside? What? I don't know how. Okay. Hopefully gets better. Okay, better? Maybe that it
Yes.
really needs this antenna outside. Yeah. Okay, so I was saying that we changed the coordinates. This is called the center of mass coordinates. And the advantage is that it does not depend on the position. But there is one more advantage that I can pick my frame to be. So let's go to the bottom one. So I can choose, right? Choose dr by dt to be equal to 0, right? So that means to say sit on the center of mass. Like wherever whoever is observer, go and sit on the center of mass, and then your velocity is gone. So and then we have only two three actually, x, y, z, and the velocities, right? So principle 6, where 6 dynamical variables, and our Lagrangian significantly simplified mu square plus g upon m2 plus magnitude of r. Are you guys losing me again?
Slightly
Yeah.
losing. Not completely. We can still make out what you're saying, but still there is some gray in there.
Is it because I'm turning around that side? No, right? I
That's when
think
it's
I'm
happening.
using. Okay, okay, still it's happening. Okay.
This
It's
is
very
fun. This
interesting
one.
that it's just yesterday I said that I was telling one of my colleagues that internet has not given me any problem all through last 10 days.
I
And,
don't think it's the internet, though. Then we would see a lag in your video as well, right? I don't think it's
oh,
the.
so it's not the internet. So you're saying it's oh.
I think I don't know.
Yeah, you must be right. Okay, so that's better. Okay. Then that's a fixable problem, right? Then that's a device issue.
Right now you sound okay.
So I hold this in my hand. So right now I'm perfectly fine.
Yep.
Yeah.
Okay, so I keep this in the hand, huh? Weird. Okay, I can hold it in the hand for some time. Okay.
It shouldn't be that, but I'm not sure.
Yeah, but that seems to be helping. There could be some like I don't like these devices. So I was telling Jordan before everyone else logged in that one would think that all these devices follow a program, which is a code line by line. They should do the same thing every time you do something, but they do different things. So they don't follow those lines apparently. So I think there is always an if command. If you don't get this by any chance, if that device is not working, then it goes to the next line. So it doesn't behave the same way. But anyway, so I think it seems to be.
Avinash says you can attach it to the T-shirt.
Yeah, it is attached to the T-shirt. Here, see. Yeah, I understood that much. Yeah. I mean, this always gives problem. I don't know why. I used to use this in room 440. Have you guys? That's a big lecture hall. And it always used to give me trouble. And that used to be a big class. I used to get intimidated that a device is not working, and expectation is that, oh, you're a physicist. Come on, you can fix it. You should know. So, and you cannot. Yeah. So okay. So let's. So now it's working fine, right?
Yeah, it's fine.
Okay, so let's let me hold it. I don't mind it. Okay, so the point is the whole idea of going to the center of mass frame was that there was a lot of coordinates and a lot of parameters or dynamical variables. And now we have reduced it to 6 in principle: position and velocity. Each of them have 3 components, so there are 6 of them, but we can reduce it further. Significantly further. That's the idea that everything happens in a plane there, right? So what we do for that purpose is, let's first use this Lagrangian and get the get our Euler-Lagrange equation, and then learn that actually the angular momentum is conserved. Even before we go there, how would you discover that angular momentum is actually conserved in the system? What tells you that, like if I were to give you any other expression for the Lagrangian, how would you conclude that without doing the calculation that it's actually angular momentum is conserved now that we have done symmetries and so on? Noether's theorem. Is the question clear?
You mean without
Looking at this
checking the
Lagrangian,
fact that without using the Lagrange equation d by dt of dou L by dou, that calculation, if that without knowing that it's zero.
without doing any calculation, just looking at it, what would you look for in the Lagrangian to conclude that angular momentum is conserved? Like, what is the symmetry associated with angular momentum?
Rotation.
Rotation, yeah. So how would you, or a better, to complete the statement, like Moses is pointing out in the right direction, but it should be symmetric under rotations, correct?
Say that again. You
By
cut off
symmetric, I got cut off again.
just for a second, but right when you said
Just
that.
for a second. Okay, okay. Yeah, this is not good. Should I just use the computer microphone? Let's try that, okay? I think I can just switch over to.
I think you're fine for most of the time.
Hello? How is this?
That's fine.
This is fine?
Except for the echo.
Worse? Is this better, worse?
We can hear you, but we can hear ourselves as well.
Oh, you can hear ourselves also. Okay. So echoing.
Just when we talk, but if we just let you talk, we'll be okay.
No. I mean, I would like it to be clear.
I mean, usually if you, well, actually, it's not doing it now.
Yeah, it seems to have stopped.
Yeah. Sometimes
just
that happens
changed the
when
factor.
your audio is too, like your speaker volume is too loud. So that it just like some feedback.
Now is
but
there an echo?
No longer an echo. No.
It's
No
working
longer
fine.
an
Yeah.
echo. Okay. That's good. Okay. So let me try to remove it from my body. How about that? Is that better? No, that should be worse.
Now
right?
the
Because
volume
mic
is
stuff-
less. It's not, I
that
mean,
is less. Okay. That's actually
yeah.
good because
I mean,
these
it's
are
still okay.
designed for only close by. Yeah. No, there is no echo.
This is fine.
We're good.
Yeah. Okay. No, my wife Prachi is trying to help, but they're saying that this mic is giving trouble.
No, I think mic might be sensitive. It might be picking up the.
No echo when I use this. It's the other way around. I don't know.
Oh, that makes sense.
Okay. I can see that there is this wireless sensor on the computer. It starts blinking whenever you guys are talking about it, and I don't know why. I cannot help it. So, but you're good now, right? So, but keep bugging me every time you cannot hear me, right? Because that's the point. Okay. So I said that. Oh yeah, I was asking, how would you look at a Lagrangian and right away, without any calculation, just by looking at it, it is possible.
If there
to
should
say
be not any theta dot dependence, right? Or omega dependence.
only theta and phi. No angular dependence.
There should be no angular dependence.
No angle. So the idea is that you look at your system in one direction, and in another direction, it should look the same. Like our universe is a classic example, except for some stars pattern there. You look from one direction to the other, it's practically the same. If you go by the density of the stars and all, it's just practically exactly the same. And that means to say that there is no angular dependence. Correct. So that means to say that there must be angular momentum must be conserved. Even like you can be very confident and right away conclude that. That's the power of Noether's theorem. Same thing if you didn't have any x dependence in this, then you can immediately say that linear momentum will be conserved. Okay, so that's immediate. So that's why the magnitude of R was important. Yes.
So that means that the angular momentum is conserved regardless of symmetry,
Yes.
even if it's asymmetric. Like if
No,
the
if it was asymmetric, then this wouldn't be R, right? See, this is magnitude of R. There is no theta phi dependence.
But I'm asking you, there you can write a system that doesn't have that dependence and not be symmetric.
And then angular momentum is not conserved.
It's not conserved.
Not conserved, yeah. For example, a system that would have that is, if the mass distribution is not uniform about the center of mass, or moment of inertia, right? Think of moment of inertia having three different components. Like think of a gyroscope going around around the Earth. So if you change the orientation, then system will change. That's one way of looking at it.
Okay.
That help. Anywhere there is a theta dependence, or put a third mass. The easiest way to break the symmetry is put a mass, then it's a reference, right? So for example, the moment I put a north star in the sky, I know that that's north. Until then, I don't have any north. Right? Imagine there are no stars in our universe. It's just the Earth sitting there, and you don't have any reference. Right? But the moment you put a north star there, then you have a reference. So you have killed the spherical symmetry.
Okay.
Right. So at this point, we are pretending that there is only one mass with reduced mass mu. Right. We have, even though it's a two-body problem, we have practically converted into a single one-body problem under a potential gravitational potential. Correct?
Yeah, I got you.
Okay.
I was just asking, like, if you had an object that was asymmetric, it could still be conserved. Like, regardless of the symmetry of the Earth and the Sun. If it was like I don't know, like the shape of a
I think
of
no,
a rock or
because for example, let us say that our Earth was not perfectly spherically symmetric. If it was a disk, correct? And if it was a finite disk, looking at the universe perpendicular to the disk is different from in the flat direction, right? So there will be a difference in whatever field is around us, or the force it experiences. Does that make sense? For example, if I were to draw this, I think I can convey that better. So for example, let's say, since we are talking about a single reduced mass, but there is an origin somewhere, right? So there is a point with respect to which we are talking about. And now we have a disk now, right? So this is a disk. And it matters as to whether this disk is perpendicular to this position or it is parallel to this position. This versus this, there will be a difference, right? So that's not spherically symmetric in that sense, right?
So in that case, you would see like a theta or a phi dependence in the Lagrangian.
There will be a theta phi dependence, yeah. So very quickly, so that's my point, that this is a very special potential. Only that case, and even that is complicated enough, and it's very rich. You change anything, things becomes complicated very quickly and not solvable. But Kepler problem is so popular. I mean, one would think that we are lucky. One way to look at it is that, oh, Kepler problem is lucky, everything is solvable. I think that's not the right way to look at it. We developed our mathematics after Newton discovered these equations. 200 years of mathematics was developed to solve the Kepler problem. So we know so many identities about that function that these days it seems, oh, you know, we are so lucky that this potential happens to be solvable. That's not the case. We studied its properties so much that we understand it much better than any other problem. That's because of need rather than it being a luck. It's not luck. If it was any other potential, like for example, these days we have our COVID-19, right? Everyone is working on it. I'm sure that after a few years, we will know about this virus better than any other virus, because everyone seems to be working on it now, right? Because there is a need for it. So something like that. Maybe the example is not appropriate now, but still the circumstance. But I convey the point, right? Okay. Okay. So with that in mind, so my point was right here, looking at it, since there is no theta phi, the angular momentum should be conserved. But nevertheless, let's evaluate the equations, right? So we have dl by dv. That's what we do first.
Can you move the screen?
Can I move the screen? Because I moved it that side and I don't come back. Thank you. Yeah. Right. Okay. So this is mu times v itself. Right? That's the same as mass times velocity. And we also have dl by dr, which is a force. Correct? I should point out that whenever I write the Lagrangian derivative of the Lagrangian with respect to the vector r, that's not a common notation, but that's the gradient. I like to write it because I think that like derivative with velocity, derivative with potential, especially when you write the Hamiltonian equations, that's kind of nice to write it like that. But it's not a common notation. It's a gradient. So don't forget that this is a gradient of the Lagrangian, and gradient of Lagrangian is basically the force, right? So this is the force, and if you were to do this, we have to do one gradient of 1 over r, right? So let me go back here. So we have to, let's just as an exercise do what is, so we are actually doing gradient of 1 over r, right? And in my notation, this is 1 over r, right? And what is that equal to?
Where?
Gradient of 1 over r.
Did you hear me?
Ah, yeah, now we can hear you, Avinash. Yes. Yeah, go ahead.
Negative vector r over r squared.
Yes, that's correct. Okay, so this is equal to negative vector r hat over r squared. Okay, so it's a nice way of doing this. So usually, explicit way of doing this is that you take the derivative with x, y, and z, write the gradient in terms of x, y, and z. But usually, if you just try to notice that the gradient of r, just the magnitude of r, remember this is a radius vector, right? The surface of a sphere. This is the radius of a sphere, right? Gradient of anything is always normal to it, normal to the surface. R equal to a constant is the equation of a sphere. Gradient of the surface of a sphere would be the normal vector of the sphere, so that's r hat. Okay, so if you see the interpretation of gradient, that comes out to be r hat. And from that point on, you use chain rule. right? Gradient of 1 over r. First do the chain minus 1 over r square, and then do the gradient of r, which we said is r hat. That's it's a geometrical way of taking the gradient instead of doing the coordinate way. You can of course do it explicitly in x, y, z coordinates. It's a lot of little bit of work, but this helps in that sense. Okay, so that's a gravitational force, right? So this is equal to minus g m1 m2. Oh, I have to change my camera orientation. Right, over r square times r hat, right? And this is also defined as the momentum p. In general, the canonical momentum, but it's a standard momentum in this case. And Euler-Lagrange equation is force dp by dt is the rate of change of momentum is equal to the force acting on the system. That's Newton's law. That's minus g m1 m2 over r square times r hat. Okay. And let me write it as r cube over r. I think it's better for this purpose. Okay. So that's you would have done this right away, right? Using introductory physics knowledge. Force is rate of change of momentum. That's a gravitational force. That's the first equation you would have written down. But using that, let's immediately ask what is the angular momentum, right? Angular momentum L. So don't confuse between the Lagrangian and the angular momentum. One is a vector, one is a scalar. So it's not necessary to change any of those letters. I think context tells you that one is a vector and one is a scalar, right? So angular momentum is r cross p. Correct? And if angular momentum is conserved, we have to take the total derivative of this angular momentum. There are two points. One is dr by dt and one is dp by dt. So there are two contributions. Dr by dt, which is velocity crossed with p, plus r crossed with dp by dt. Okay. First one is velocity crossed with momentum, but momentum itself is mu times velocity. So this is, I can still write one more line, I suppose, there. So this is equal to velocity crossed with mu times v, right? Momentum is mu times v, plus r crossed with the force, which is r times g m1 m2 over r cube. And this clearly brings out that angular momentum must be conserved. V cross v is 0, r cross r is 0. So that's surely 0. Okay. So that's a explicit way of seeing it. But again, you should be able to look at right away in the beginning of the problem that there is no angular coordinates. That means there is no angular. That's called based on symmetry. So especially when you're doing a new problem, you don't want to work with too many parameters. That's also like all of you guys invariably will do some kind of modeling or research problem in the future, even if it is not in a fundamental research. You always work with some parameters. One thing one should realize is that any model that has more than 3 parameters is too much. too much information to process. Okay. 2 parameters is perfect. I think that can be done. 3 parameters can be done by most of the people around us. 4 parameters, you need an extremely smart person, and probably the smartest person born can deal with 7 parameters at a time. And weather model has 17 parameters. Okay, so the weather model that we predict things with, that has 17 parameters. Standard model, which is the most successful model in physics, has I think some 23 or 27 parameters. So it's very, so people work in a they fix 24 of the parameters, pick 3 and work in that. That's how usually it works, because ability is only that much, at least to bring out your thoughts. It's hard to work with more than 3 parameters. So that's just
you're
based
talking
on
about this
experience.
manually, is it?
Huh?
Are you talking like this many parameters only humanly possible? Manually we can work, or computer in a computer?
What can you, no, see, you need to analyze, right? Computer cannot analyze for you. Computer can only tell you what you ask it to do, correct? Eventually you have to ask that, okay, if I change something, what will happen to the other parameter? Right, that's analysis. You say that, okay, suppose Earth is at the closest to the sun versus farthest to the sun, what happens? So you change one parameter and look for how the system changes. Computer can give you a graph if you ask it to plot it. You see what I'm trying to say? There is a lot of information on the computer, but unless you ask it to give the right thing, it won't give you. Does that make sense? Did I convey the point? For
Yes,
example, I think the best example is CERN, one of the accelerators we have. That generates lots of data, lots of information in there. But you should know what you're looking for. Otherwise, you won't find it. There's probably a lot of information in there, but it will give you only what you search for. It's, I mean, usually you call it searching for a needle in a haystack. It's even that parameter, you have to spend a lot of effort and energy. You have a whole team, actually a factory of people working on the data to get that particular needle, but you're searching for that. If you don't search for the needle and say you were supposed to search for a hammer and you're searching for the needle, you will never find the hammer, right? Think of magnetic monopole. That's a good example. It might be sitting right here in our room, but unless we know how to look for it, we may not find it.
So even a computer's algorithm cannot find it. Is that what you're saying? Even let's say we have a supercomputer or something which has a very high efficiency.
But
he's saying you have to program. You would have to program the computer to search for it. So unless you in your mind knew those 23 or 27 parameters itself, you can't actually write a computer program to search for something that's not written. Does that make sense? So you can only, he's saying that the typical humans like us maybe can only consider 3 possible areas, but there's 27 parameters in some models, and unless you can physically capably think and reason through 27 parameters, you can't write a program to search for those things. Does that make sense? I don't know. I think I get it.
Maybe, yeah.
Yeah. Hopefully, I'm not overstating it. I think. Or okay, let's.
Well, when we have sentient computers, then they can do it for us.
That was my question. Let's say our technology is so far advanced that I'm just questioning if knowing the number of parameters is like something that only human brain can understand, something like that. Like, is this the maximum that we can potentially reach even in the future, or is something that we can code so that we can? That was my question, I guess. Maybe more of a side thinking, but yeah, that was my question.
Like, okay, maybe what I'm saying is that we look for patterns, right? I think our human mind, I think when we say what is science, my personal view is that we look for patterns. And if we can teach the computer to look for patterns, that might do the job, yes. But that I think is hard. As of now, it doesn't exist, to my knowledge, unless the pattern is too trivial. Like it's like saying, or even the pattern, we have to tell, right, which pattern to search for. Right there, the bias comes in. Oh, look for circular pattern, circular rings in the sky. Like think of, put the whole star pattern on a sheet of paper, and then you ask, is there a pattern in this? What do you mean by a pattern, right? If you were to ask the computer to find a pattern for you, you will say that, okay, look for circular pattern, but that's a bias. Circle is your pattern. Do you see what I'm trying to say?
So that's similarly the
Dependent. You're looking
point.
for patterns, bias there.
But again, if you choose any 3 stars, they will make a circle.
Yeah, good point. Yeah, probably a bad example, right? Yeah. Or all possible circles, and if that is no, I don't want to say anything. Like what I'm trying to say is that that's a thought process in which you will go, but our mind goes through it in a certain manner. Computer can do it, but I think that's what is called by artificial intelligence in the serious sense, not going by the standard terminology that these days we use. It's used in different sense, I think. But I think.
So like,
yeah.
Oh, go ahead.
You can go ahead.
I was just gonna say, like, Angela, if you think about the AI with chess, so there's 2 traditional models for chess computing that they do. One is like a brute force method where the computer crunches numbers to some huge number to try to figure out what's the next best move. Well, they've created now an AI that instead of crunching those numbers, plays against itself and tries to learn patterns that are that play out in games that it plays against itself, and then also with other humans. So until like you can find some AI that can parameterize 27 possible thoughts simultaneously, then it's not possible. Otherwise, we would know like tomorrow it's going to be 64 degrees because it's parameterized in that fashion. But right now it's just like, hey, it should be about 65 to 73 tomorrow. Does that make sense? I don't know. I think I get what you're saying.
Yes, yeah, that's what I think I'm saying. I don't want to stress on it too much either. I think the only one comment I will make on that is like, let's think of dark matter, right? What do we mean by dark matter? Like it could be between Earth and the sun, or for that matter in your room, correct? But we don't know how to detect it. We know that there is a proton existing because we know that it's positively charged. You will bring a negative charge to detect it. If you don't know what are the properties of that quantity, you don't know how to look at it. Does that make sense? And the same thing I'm saying as far as the computer goes, unless you look for something, unless you know what you're looking for, you cannot look at it. A philosophical statement. I didn't mean to do philosophy. Yeah.
How I see
Does that
things
help?
is,
Yes.
how I see things is the computer is as smart as the person using it.
Yeah, to a certain extent. I do agree that it can do a lot more than what a human can do as far as processing goes, but you have to tell it to process it. You have to first of all
exactly. If you don't know how to process it.
Isn't that the achievement that we're making right now, that computer can make analytical decisions and it's not just about processing anymore? Isn't
But
that
it's a human
Boston
student,
robotics, right? And all that stuff, all of their hurdle crossing robotic animals and stuff like that?
Agreed, but only to a certain, I mean, we haven't reached the level where it can do great things. Hope is that it will do it. It is not as intelligent as we would like it to be. Do you see what I'm saying?
It's not writing
Yes,
its own code to do things. It's not programming itself.
I think that's what they're aiming for in artificial intelligence, but we are now, I mean, of course, we have made great progress and expectation is that we will do a lot, but my understanding is that we haven't done great. I mean, there is a lot more room there. And
Yeah,
another big question that comes in, I think all these are good for you guys, the sense when you think of research projects, these are the things you want to look for. One thing that's a big hurdle in artificial intelligence is it scalable? Like it might be able to do a very small thing much better than humans, but can you do all what human can do together? So that means to say that, okay, for example, you have a processor. If you're using all the processor speed, very expensive supercomputer, as you use the word, for doing some very trivial job, that means it's not scalable. You cannot expect to have thousands of supercomputers for one minor job that it will do. So scalability is an important thing, and that becomes a constraint in most of the situation. In other words, economically, is it possible? Or even not just economically, it is physically, it is possible or not. But yeah, let me not say too much. I might be wrong. I might be too behind the time maybe. Okay, but look it up. So I hope I conveyed the point. Okay, so shall I, why did I go in that direction to begin with? Oh yeah, I was talking about we had 6 plus 6, 12 parameters to begin with, right? So there was 2 positions of 2 masses, 2 velocities of 2 masses. One would think that there are 12 parameters, like 6 positions, 6 velocities, but they're all not dependent. We got smart and immediately we got rid of 6 of them. And then we want to get rid of some more, right? Now there are 3 positions and 3 velocities. Now we want to point out that angular momentum is conserved. So that means there is a direction. So what does angular momentum conserved mean? There is a direction which remains fixed for the system. Okay. So pick that direction to be the z-axis, let's say, just because we can choose. So choose L along z-axis. And one should track this. Remember, we have already set our coordinate. We have first chosen our origin, right? We decided that we will sit on the center of mass. And now, once you're sitting on the center of mass, you have the ability to rotate your z, x, y, z, right? First, you set your origin, and then you choose your axis. So origin is in the center of mass, and the z-axis you choose along the angular momentum. What decides the angular momentum? What decides angular momentum to begin with? So initial conditions usually. Like somewhere the system begins rolling, right? If it was just 2 masses in your laboratory, then you would initiate by letting one of the masses go from your hand, right? So that is an initial condition there. That decides your angular momentum, in which direction you push it or in which direction does it start moving. That decides your angular momentum. And that motion typically decides your z-axis, right? Since L is R cross P, right, you know that R is always perpendicular to L, right? If you choose angular momentum to be on the z-axis, R has to be perpendicular to that. So R is in the xy direction. So that implies that R is perpendicular to angular momentum. So that implies that it's in the xy plane. Right? The position of this of this reduced mass, that abstract point, is moving, and that is always in the xy plane. That is equivalent to, if you, since we sort of alluded to magnitude of position vector. So that means to say that if you're in spherical coordinates, choose theta is equal to pi by 2. Theta is the angle between the position vector and z hat, remember. So r hat dotted with z hat is cosine theta. I point out that because in mathematics usually use the angle with respect to the z-axis is angle phi. Right? In spherical coordinates you have r theta phi. So now we have theta is chosen to be pi by 2. So you're in the xy plane. So the parameters that so what that means is that L now depends only on r, the magnitude of the vector. So you're working in polar coordinates now. Angle phi, because you're on a plane, you can actually use cylindrical polar coordinates, r phi, and it will change. R can change, r dot, and phi can change, so that's phi dot. Right? That's your coordinates. Is that clear? Okay. So now we are in 4 coordinates. Even that can be reduced, right? I said 3, right? 3 is the easy thing to work with. I didn't count it before, so. Any questions at this stage? Okay. So move this. Come on. Okay. So remember L is L of r phi r dot phi dot, right? That's half mu velocity square plus where is our angle Lagrangian? So plus g m1 m2 over r. Velocity, both velocity and r is in the xy plane. What's velocity in the xy plane? Let's work in polar coordinates. Velocity, we have done this before, right? So velocity is help. So this is r dot square plus r square phi dot square. Okay, and how do we see that? Yeah, I think how do we do that? So velocity. So sorry, this is velocity square. So velocity square, if you want, is the same as x dotted square plus y dotted square. And x is equal to r cosine phi, and y is equal to r sine phi. Right, with respect to the origin. So x dot is, so we will have 2 of them, right? So x dot will be r dot cosine phi plus or minus, actually minus r sine phi dot. And y dot is equal to and if you were to square this, so x dot is square plus y dot is square. The first square terms sine square plus sine square makes it r dot is square, and the second one, when you square it, you get r square phi dot square, again sine square plus cosine square is 1, and there are cross term which exactly cancels out. So that's all that survives, right? You have used this sufficiently in other problems that it's just a repetition at this stage, and understand that. Okay, so our Lagrangian again is r phi r dot phi dot is equal to 1 by 2 mu r dot square, correct? And then there is 1 by 2 mu r square phi dot square, and then there is plus G M1 M2 over R. Correct? I said we will have 4 coordinates here. There is R, phi, R dot, and phi dot. On the right hand side, what is missing?
Phi.
There is no phi, right? There is no phi here, so that's not there. What does that mean? Whenever there is something is not there, that means that doesn't depend on that. There must be some symmetry. Right?
Angular momentum conservation and phi.
Angular momentum, right? So when I chose my angular momentum to be in the z direction, I still have the rotation about a z axis available to me. So that means that angular momentum is conserved. So that's that information. So we have only 3 coordinates, but now we can write our equations of motion with the idea that that is not there. So there will be some conservation, something will be conserved, and that will be angular momentum in the z direction. So LZ if you want, correct? So now let's, at this stage we can, so our everything now will depend on these 3 coordinates. So R, R dot, and phi dot. And out of that, one of them, so our phi is not there, so phi dot will be conserved. So there will be nice features coming out still. So let's do so dl by dv, let's say. Let's dv, yeah, it's okay. All right. So this is your, what should I call this? Let's write r dot. Let's not confuse. So r dot. So that's equal to mu r dot. That's your radial momentum. Right. Let's call it PR. And there is phi also is there. So dl by d phi dot. That's equal to mu r square phi dot. And this we will call it the canonical momentum with respect to angle phi. And what's the
Can you move
dimension of
the-
this?
Can you move the screen
Oh,
down?
oh. Forget. Sorry, thank you.
That's okay.
Okay. So I first wrote the momentum, generalized momentum with respect to the magnitude of the vector r, right? That will be your radial momentum if you want. So that's mu r dot. And then there is a generalized momentum with respect to angle phi. That's mu r square phi dot. What's the dimensions of this? What's this quantity?
kg meter square per second square.
Yeah, but what does that physical quantity mean? What is that physical
Energy.
quantity?
Energy, Newton meter, energy.
Try again. Yeah.
It's
Is it
angular
energy?
momentum, right?
Angular momentum, right? Angle phi, it must be angular momentum. Does angular momentum and energy have the same dimensions or what?
I don't think so.
No, right? No. So probably Avinash here, check. This may not be Newton meter.
It'll be distance times normal momentum units, right?
I'm sorry.
Yeah.
I was thinking R is meter per second. That's why I made a mistake.
Yeah.
It's kg meter square.
Okay. Yeah, so that's angular momentum in the z direction, right? So this will be the, or you can call it canonical momentum with respect to angle phi. That turns out to be the angular momentum. What about the force? This will be dl by dr, right? There are 2 places where it comes up, right? Before that, let me do dl by d phi. So the easy one. What is the change in angular moment? Change in the Lagrangian with respect to angle phi. The easy one, right? No angle phi, that's 0, right? So no torque. That's it. So this is the radial force. Radial force, of course, that is gravity, but there is one more term that is showing up. What is that? The radial force is the usual, but this is with respect to the magnitude of R, remember? So that's minus G M1 M2 over R square, but there is an R here also. Don't forget that. So that's plus mu R phi dot square. What is that term? In introductory physics, what does that mean? Mu R phi dot square. Why is that showing up as a force? When a mass is moving around another mass, there is a gravitational force in the radial direction, correct? Why is there another quantity there? What does that mean? Like, why do we have this?
The centripetal force.
Yeah. What is that? Yes. Centripetal force, but now it is showing up as a centrifugal force because you are, let's say, that's a inertial force, if you want to say. I think centrifugal force. Yeah, correct. That's that centrifugal term there. Usually, we don't use the term centrifugal in introductory physics, right? We try not to use that word so that it doesn't confuse students. But now that's that force in there, inbuilt there. Sure, good. So Euler-Lagrange equation. First of all, there is a conserved quantity, or first let me do it in order. The d by dt of R double dot, right? Let me not write anything. So this is, so the main equation is mu R double dot, right? Mu does not depend on time. That's equal to minus G M1 M2 over R square plus mu R phi dot square, and d by dt of this is constant, so we will just say mu R square phi dot is, so time derivative of this is 0. That means to say that that's a constant. We will call that LZ. That's a constant. LZ because it's angular momentum in the z direction. That's your two equations of motion. Okay. So here is a question. We have an attractive force acting on Earth, correct? Sun pulls it towards it. Why doesn't it collapse into the sun? Why is it stable? Why are we stable here? Like, Earth keeps going around the sun in the same orbit again and again, correct? Why is it stable? Why don't we just crash into the sun? It's attractive force. Something is pulling us. Like, whatever you guys have in your mind is correct. I'm not, I think most probably all of you guys know it.
It's just the inertia. The inertia that we have moving in the direction that
the centrifugal force kind of balances it, or another way of saying it is that we are keeping on falling. That's a language one uses, but in terms of our, so that's your centrifugal force. That's necessary to balance that. So if you want R double dot to be 0, in a sense, if you want it to be stable, the radius should not change. Then if it was circular motion, for example, then R doesn't change. Then you want this to balance each other. So circular motion will correspond to these two exactly balancing each other. But elliptic motion, it doesn't balance all the time. There is a, it fluctuates around that radius. Okay. This seems to have a phi dot. Oh, I have 5 minutes crossed. So yeah, I think this is a good place to stop. We'll start from this point, and now we have our differential equation. So eventually we have boiled it down to a plane R and a phi. Further, phi dot is a constant, so we can solve this differential equation. And obviously, the solution of this equation is a conic section. Okay, since we learn it as Kepler's law that the solution must be conic section, but we will see this. We'll derive the solution, and from that point on, we will analyze what are the elliptic orbits, what are the hyperbolic orbits, parabolic orbits, and circular orbits, how it comes about. Okay, any comments, questions? Thank you. How was the audio afterwards?
It held up.
Mostly better, yeah.
Okay, better, but not perfect.
Yeah, there was a little bit of like a few seconds here and there. There was just some crash, but I think it was fine.
Okay, okay. Yeah, I hope I don't have to hold this all the time.
Oh, you're holding the receiver?
I'm just holding it like, where am I?
Oh.
I was, it's so like as if I'm speaking to this.
What happens when you put it in your pant or like shirt?
It should be in the pant, but then I felt that whenever I took it out of my pocket, you guys stopped complaining.
Is there not a clip on it?
Huh?
Is there not a clip on it?
There is a clip. Where is it? Where's the camera? Yeah, there is a clip on it. And I was putting it inside of the pocket, and this is too tight. So even I tried that also. I clipped it on for sometime whenever we were discussing, but it didn't seem to work. And eventually, when I was holding it in the hand, you guys stopped complaining. But I don't think that.
I wonder if I wonder if the wire, that part.
Loose. Yeah, usually that's
I just wonder if that, or if the receiver itself is bumping your pants and then causing like a static or whatever. So maybe if you clip it on your back pocket, like on the outside, like if you clip it on your butt.
Yeah. Yes,
Maybe.
Moses?
Oh, I was just gonna say, like, try bumping the antenna.
Do you have a T-shirt with a pocket?
And speaking at the same time, and see if that. So just like figure out what is causing the disruption when you're speaking.
Oh.
Like what causes?
Hello?
Yeah.
Hello?
When the antenna is bumped, it's your audio starts
giving you trouble.
Yeah.
Hello.
Well, I don't have any trouble.
So
yeah,
hello.
I was hearing
hello
for a second. Yeah.
Hello.
Yeah, there you go. There's a little bit.
That is a problem.
Mm-hmm.
Yeah.
Not for me.
So I have to leave this very sensitive. Huh? It has to be not touched. That it has to be outside.
Do you have a T-shirt with a pocket?
Oh, T-shirt. No, this T-shirt doesn't have a pocket. I can put it here, or I can. I can. Once I've discovered that this is a problem, then I just have to find a way to clip it so that it doesn't get touched. Right. That's the main thing, I think. I was just putting it in my pocket, and even when I was clipping it, it was not perfectly staying outside. So I had to make sure that I keep it. I think there are easy ways to do that. Yeah. Yeah. So this is okay. Good enough. Yeah. I think I put it on my belt. I think that works good.
Sounds good.
Okay. This helps. Yeah. Figuring out. Otherwise, I don't have any audience, right? I cannot explain them. Yeah. Okay, thank you.
So you were going to answer something for us, but I forget what you said you were going to answer today.
Huh?
You said.
Oh yeah, it's about that two charges thing, two moving charges. So where is the momentum going? That question.
Yeah.
Oh yes, I said that. Yes, good. So the hint is I cannot prove this for you guys very quickly. In fact, this very quickly leads into an open area of research, and that is field. There are two charges, and there is electric field and magnetic field all around it.
Mm-hmm.
And electric field and magnetic field have both energy in it and momentum in it. Is that clear?
Yes.
So two charges are not on their own. There is a field around it.
Okay.
And that's a challenge with gravity. Gravitational field is significantly much more complicated because it's a tensor field. What is the momentum associated with the electric and magnetic fields? What is the momentum associated with electric and magnetic fields?
Or momentum, relativistic moment? No.
It is E cross B.
Oh, the
Cross
pointing.
product of E and B is the momentum.
Oh, yeah.
So
Yeah. The
whenever
pointing.
you have electric and magnetic field together, there is a momentum usually. Okay. It may not be time dependent. So momentum is there. If there is no time dependence, it won't experience a force. What is the energy associated with electric and magnetic fields?
1/2 epsilon naught E square.
Yes, E square plus B square, half E square plus half mu B square, right? The energy inside a capacitor is the electric field energy, and energy inside an inductor is the magnetic field. It's stored in the form of a magnetic energy. Good.
So is it possible to like arrange them in such a way that the particles interact where their mechanical momentum isn't conserved then?
yes, it is. Yes.
It is. Okay.
And in the literature, again, not blaming anyone, sometimes they ignore this, and you see a lot of wrong things written because they will say, oh, we have not conserved the momentum. So often this is also discussed under the word hidden momentum. So if you look up hidden momentum, there is a lot of literature on it. Usually controversial literature because it's a little subtle in the sense it's easy to miss things. It's easy to conclude that things are wrong or the electromagnetism is not complete and so on, or it doesn't obey conservation principles. So, but the key is, I've not given you the answer why, but when we talked about action-reaction forces there, we didn't do a complete job because fields are involved, which has momentum and forces associated with it. But that's the biggest challenge, and especially with gravity, that field is there everywhere, correct?
Mm-hmm.
And what do you mean by conservation of energy after that? If the field is there everywhere around. So it becomes very difficult to collect all your energies. Every point in space and time has energy and momentum. So it's very hard to build a mathematics to deal with it. And that's field theory, if you want. That's called quantum field theory. You might have heard the topic. And quantum field theory for gravitational physics is challenging, to say it lightly. Yeah. Okay. Is that?
Does anybody else
yeah,
see a filter in the video?
Yes.
A bluish green filter?
Yeah, I noticed that this is in the last 5-10 minutes, right?
Oh,
it just
went
it's
away
back
now.
to normal again.
Huh, what is happening? I don't know. What is happening today?
Put your move your red shirt back in the frame.
Oh, it is that, you think?
Can you
that is the point?
can you take that receiver in front of the camera?
Receiver
It
of
might
that.
be because of the magnetic field.
Put it really
Some
close
funny
to the
things
camera.
happen, right?
Put it really close to the camera.
Or around the computer.
Or around the computer, yeah.
Nice. Yeah, I also noticed that, but then I was thinking it's only on my TV and not there. And that was right after I put it on my belt. This microphone has issues, huh? This is a new microphone department bought for us. One would think that this, yeah, but at least
I think there are just limitations to the technology. And when you use two different technologies in conjunction with each other, then more complexities arise.
Yeah. Especially with me,
more than
I-
three
I-
parameters.
Yeah, there's 4 parameters in this one, so we can't understand.
Well, 4 parameters. Don't take it too literally.
I can only understand 1 parameter.
That's what I tell with my friends. I'm a pretty one parameter person. Dumb. No, sorry.
Okay. Well, thank you. And
Yeah, thanks.
Okay, enjoy, guys. Yeah, thank you.
Bye-bye.
Bye.
I actually have one more question. If you have a
Yeah, sure. Go ahead. Yeah.
Okay. Well, it's on the second problem of homework 6. It was
Second problem on homework 6. Let me pull it out. Let's see. Oh, yeah, this is symmetry. Yes. Okay.
Yeah.
Go ahead.
So on part B, I was trying to use the generator, and I was just getting a sign error again.
Oh. Did you make sure Hamiltonian Lagrangian?
Well, yeah, the Hamiltonian Lagrangian should have opposite sign.
Yes.
Yeah, and that's
So part B.
so part
Yeah,
A, I
right.
get the right sign. But then part B, if I just start with the generic form of the action with the generator,
Okay,
and then I plug in, the first part of the generator with delta R dot P is 0.
Yeah,
Then we have a negative delta T times H.
Give me a second. Let me reach there. Okay, Lagrangian. So dW should be minus that DH. Let's see. Oh. I think there is an error. Okay, let me see again. Hold on. Oh, that's because, yeah, relatively speaking, yes, there is an error in that.
Okay.
Yes. Yeah. I think there is a difference, I think, is the following. What I think there might be, relatively speaking, an error, but I know why that has happened if there is an error. So, visible?
Yeah.
Yeah. So I think that is this transformation we are talking about, T prime is equal to T. We can either define it as plus delta T, or you can define it as minus delta T.
Up a little bit.
Oh, up a little bit. Why is that? Huh. Really?
Okay. Yeah.
I thought this was set. Okay. Good?
Yeah, that's fine.
Yeah, okay. So I can either define it this way, or I can define it this way. And I think in the problem, it is not very clear, ambiguity, because I didn't mention it. And in the class, I use this, I suppose. Agreed? That was a quantity I defined in the class. And when I wrote the problem, I'm noticing that I had used this. So anyway, so the point is, yes, there is that when I'm right away looking at problem A and problem B, I'm seeing that there is a sign off.
Yeah. So
is everyone there? Oh, Jordan, Avinash?
Yep, I'm here.
Yeah.
Angela? Okay, you guys are, so yeah, so this is good. So I can announce it to everyone that there's a sign error in part B of problem 2, I think. Okay. I think if you compare it with what's done in the class. Yeah, good.
So did you upload that part onto YouTube, that class? Because I actually wasn't there for that class. That was, you did that during the spring break, I think.
No, that was not a class. No, that's not what we're discussing. This is before that. This is the day before the spring break.
Before
He-
We
spring, the
derived
very,
the whole Lagrangian.
He
Or-
had
or
some
the-
problems with his car, so he did not come to class.
Oh, yes, that was before the spring break.
I
Remember
think,
that.
Moses, I think you sent
Oh.
that to me then, right?
Yeah, I did.
Okay, great. I got it then. I just need to go through it.
Oh. So you probably have the notes, right? I don't think it was recorded.
Yeah, I
No,
think
I sent him the notes.
I'll just have the notes. I need to
Yeah.
just take a look at those.
Yeah.
Okay.
And the book by book on electrodynamics by Schwinger. I think it's chapter 8 or something that discusses it, this part, but not exactly the way it is, but I expand on it. I think that's the way to put it. Everything is there. So this is which chapter? Let me see. This is the book I'm talking about, right? I use this for electrodynamics in our department, but if you're not familiar, I think that's where it is taken from. Let's see. Yeah, invariance and conservation law. So it's chapter 8 of. So if you can always come back to this recording and see, right, if necessary, at the very end of the recording. Assuming we have
Now
a
you just need to open every page so I can copy it.
if you want, I can photocopy the chapter and send you.
That's okay.
I'm allowed to.
I think
I'm allowed to do.
it'll be online.
I'm allowed to do one chapter for the students at a time. And in principle, I can do that, split it into every week, and I think in principle that's okay. But I cannot post it, the whole book.
Yeah. No, I can find it online. I just go through it there.
Okay.
Is
Yeah.
that book even copyrighted?
Yeah. The author is alive.
Oh, he is. Okay.
I mean, 3 of the authors are alive. Only Schwinger is not alive. Schwinger is no more, but other 3 were his students. So they are all alive. They're all old, though. Old in the sense relatively, right? Yeah. These days, if you consider 75 as old, yeah.
That is old, pretty old.
That is old, yeah. With respect to you guys, everyone is old. I'm almost halfway in the grave with respect to you guys.
Not me.
Oh, yeah.
Hey,
Um,
hey, Jordan, you are old.
I know. My parameters reduced by 1 each year. On that note, I gotta go.
cool.
Goodbye, friends.
Okay, yeah.
I was just going to point out that
Yeah.
what we talked about yesterday, Shajesh, there was one error in the notes from class about the action,
Oh,
the change in action, and
in
just
the
like
class.
yeah. Well, this was the. I don't know if you can see this, but this is the one.
Oh,
We had those as being
Yes.
opposite sign, but they should be the same sign.
they should be. Oh, you mean to say I said to be the. No,
In
tell us
class,
again.
yeah, in class, I wrote this was written down as having. I added that plus sign,
Okay. Got it.
so now it's correct. But it was,
Okay.
yeah. I don't know.
Okay, good.
It's like,
Could you do me a favor? Could you send me any? I mean, will you feel comfortable sending it to others?
yeah,
What is it
I'll do
about?
that.
Information?
What is it
Yeah,
about?
just so that I requested you to do that.
Sure thing. Yeah, I can do
Right?
that.
If you feel uncomfortable, yeah.
That's no
Thank
problem.
Because that might help others. Just they need to keep a watch on it.
Right.
I expect you guys to go through it. I'm fine with making mistakes, but gives a, it helps others if they know that there is a possibility of an error.
Right.
Yeah.
Okay. Yeah, I can do
Which
that.
part are you
No problem.
talking about?
This was on after the Thursday lecture of, this was before spring break.
Oh,
It was,
before spring break.
It was when we derived the change in action, like the complete change in action form, and when we derived the expression for the generator.
Okay.
It was
hard to-
from
it's
the
hard to
5th,
find
March
it.
5th, Thursday, March 5th was the lecture.
I don't know.
Which made sense with the relative signs between H
Is
and
it
flow, right?
under symmetries and conservation principles?
It's just before that.
Just before that,
The
stationary
generator,
action
like-
principle.
Yeah, stationary action principle, and then just above stationary action principle, or just before that, was when we wrote down the complete action in terms of three different,
Oh,
the sum of three integrands.
okay.
I
I see.
And the argument of two of them was delta W by delta R
Yes.
for one, and then delta W by delta T for the other.
Yes.
And there's, in delta W by delta T, I wrote down in class that dH by dt was negative,
Yes.
and it should be positive.
Okay.
And then also the last term in the integrand, it should be positive. dH by dt should be positive, and the whole integrand should be positive, rather than
Oh,
yeah.
Oh, I see. There was a negative dt.
Yeah.
dt.
Yeah.
I see.
Yeah. So I'll take a picture of my notes and send that
Yeah.
out.
And what was the source of the error? Do you know?
Well,
The source of the error was this. You know what? I think it is.
Randomly or
I think
while
it is okay. Because there is a different, like, the second term is a positive sign, so it means one is negative sign and the other is positive sign. So I think it is correct.
well, the thing is, we want d by d or dH by dt to be the opposite sign as the partial of the Lagrangian with respect to time. And if
we get it right. So we get negative the partial derivative of Hamiltonian with respect to t plus partial derivative of Lagrangian with respect to t. So those two are negative signs because this this v dot dl over dv minus l, this whole thing is h. So if there is a negative d over dt in front of it, that makes it negative dh over dt.
no, I got that, and I think the sign error happened probably earlier than that.
Earlier than that, and I guess I'll have to.
I don't know that it's like, it might have to do with what you like. It's a good question. Should go and try to find it, because it. I mean, I'm wondering if it has to do with the convention that you wrote of choosing T prime.
Oh, no. No,
No, it doesn't.
no.
Okay.
In the class, stick to the notation that's followed there. It's only when the notes come into picture, because in one year I might use one notation,
Yeah.
and in another year I might use another notation. So whenever I framed the question, that may not be the year in which I've used a certain notation
Okay.
in the class. So there could be a difference between the classroom and the homework. That's possible in notation difference. But inside the classroom, there shouldn't be any change, because I
Right.
usually don't use my notes.
So in homework 6, which notation should we use? So should we use T prime equals T
Look
minus
into your class
delta
notes.
T?
Right in the beginning, somewhere I have written that. I don't remember. Use your class notes right in the beginning of the week before spring break. We began something.
Yeah, when we started covering the stationary action principle.
Yes. So most probably, I think if I recollect, I used T plus delta T, but I don't remember.
You
And
said let T prime be T minus delta T.
Okay.
I see it now. Yes, we used T prime plus delta T. T plus delta T.
So I'll leave that to you guys.
Okay.
Okay. But I mean, if you want, I can clarify it if it is leading to more or more trouble than helping. I can fix it for you guys. But as of now, I'm not trying to. Okay.
Yeah, that's fine. I guess
Yeah.
I'll try to look through my notes and find out where that sign error came in then.
Yeah. I think that might be the right thing to do, because I can see that my notes are consistent.
Yeah.
But I don't have the class notes with me.
You don't have the class
So
notes?
I don't, because I just do it in the class, right?
Oh, I
don't,
see. Yeah. Okay.
Unless I use your notebook,
Right.
I cannot do that.
Okay, well, I'll try to
why
go
I
through it
cannot.
again and find it.
Yeah. But I can always, I should be able to fix it immediately if you want me to, okay?
Okay.
If there is more than 5 minutes of discussion on this, that means it's not good. So
Yeah.
we'll fix it for once, okay? It's always
Okay.
possible that I made the error in the classroom. I'm not saying that I don't make errors, but just don't make wrong conclusions. That's all.
Right, of course.
Yeah. Okay, good.
Alrighty.
More questions?
So just for like for question B, part B of question 2 on homework 6, just it should be the opposite sign. Just leave it as.
Yes, that should be, because the Hamiltonian is equal to P r dot minus L, right?
Right.
So H and L, if they are sitting on the same side, they should be of the same sign. And if they are on the opposite side of the equality sign, then they should be of the opposite sign. Correct?
Yeah.
I think that's how it will go.
So yeah, so it'll agree with part A then. Whatever is true on part A, then part
But
B.
I do feel that there is an error in that homework. I agree to that.
Okay.
So I'm not denying that. Part B that you pointed out,
Yeah.
that I agree. But the notes one, I'm not sure about.
Sure.
Okay.
So regarding, so yeah, so it can just, our sign doesn't, for that particular question, the sign doesn't have to, it should not agree with what you have in the assignment.
Exactly.
Okay.
Okay, give me 1 more minute. Since I have this book, I can at least look into that, right? So you were saying dH by dt and dl. Oh, but that doesn't show up here, right? Okay, your equation, okay, minus plus. Yeah, it will be dH by dt plus dl by partial derivative of L with respect to time will be equal to 0.
Yes.
Both the same sign when they are on both the same,
Yes.
both the terms on the same side of the equation.
Yes.
They will have the same sign.
Yeah.
Okay.
So then,
Okay.
yeah,
Good.
exactly.
Okay.
And that's not what I had written in my notes.
Okay. So then there is an error in there.
Yeah.
That notes. Yeah.
So,
It is class notes.
so is it positive? Plus dH
Okay, let
over
me write it
dt?
down. Okay, we have a board here, right? I can write it down. So dH by dt is usually equal to partial derivative of dt, which is equal to minus L by dt. Okay. Which, if you write it on the same side, plus. With you, Moses? Do you?
Yep.
Right? Yeah. So this seems to be correct. And apparently this was not written on the right, with the right signs in the classroom.
Correct. Well, yeah, because so the bottom line that you wrote is also equal to the change in action with respect to delta t.
Oh, let's see. Okay.
So,
I don't remember it right away. Hold on. Yeah, it will be, right? It has to be.
yeah.
Yeah, agreed. Yeah.
Yeah. And in my notes, they had opposite signs.
Yeah.
Which meant that they were equal to each other, not so the partial of the Hamiltonian with respect to t was equal to the partial of the Lagrangian with respect to t, and they should be opposite signs.
Yeah. So then the question comes, what happened in the class? So usually typically often I do is that when I'm copying an equation, I make an error.
Mm-hmm.
So that's a possibility, but I hope I didn't make a conceptual error. That's the only thing you want to be careful about. But I don't see any room there for a conceptual error. But just look into your notes and see if going from one step to the other, I skipped a sign or something. Then that's a typo, but hopefully not a conceptual error. And the transformation delta t notation, that cannot lead to this because it's a relative sign.
Okay.
So it cannot lead to this problem. So this is some other issue there in the notes, the class notes.
Gotcha. Okay.
Yeah. Okay. Good. Okay, guys.
All right. Thank you.
All right, thank you.
Okay. Enjoy. Good luck.
All right. Thank you. Yeah, you
See
too.
in St. Louis, Moses now.
Oh, thanks.
Bye.
See you later.
Okay.